Hello, my name is METİN ARIDAŞIR. This is for the sixth part of explanation of my theory. There is a mountain where a pine tree is rooted in. Compton's experiment attempts to cut this tree by means of Bragg-like crystal to investigate it independent from the mountain. But this experiment failed to cut the tree wholly, and still the tree transfers the variations from the mountain that is rooted. Here the pine tree is a characteristic ray. The mountain is the continuous spectrum. Again, there is a mountain where a pine tree is rooted in. Compton's experiment attempts to cut this tree by means of Bragg-like crystal to investigate it independent from the mountain. But this experiment failed to cut the tree wholly, and still the tree transfers the variations from the mountain that is rooted. Here the pine tree is a characteristic X-ray. The mountain is the continuous spectrum. Here crystal. Yes. Here a balance cosine alpha. Next I will tell you. From here. Snapshot, I guess. This is good for you, for taking a photograph. Stop the video and look at that I wrote according to my formulas and my theory. Yes. And here for another snapshot according to my theory and my formulas. I will tell you step by step, again and again, I guess. Blue dots circle is single wave pulse that coincides with black circles at certain wavelength. Black circles from relocating free electron motion forms successive waves. They are free electron motion forms successive waves. Okay. Here, crystal, Bragg-like or Bragg crystal, Bragg crystal, Bragg crystal, Bragg crystal. Okay. Here my formulations, I will tell you now. Okay. One, Compton experiment resultant peaks. Here crystal, front of crystal side for successive waves of free electron motion forms results. Behind of crystal, single wave pulses that passed filtered from this or this or this crystal at a certain angle, say 45 degrees, say 90 degrees, say 30 degrees, etc. For each angles, okay. Here determinative is successive waves, relocating free electron motion form. Okay, these are the determinative for varying on single wave pulse wavelength shift. Okay. Compton experiment resultant peaks, two peaks, one of real single wave pulses wavelength, unchanged, first one unchanged, okay, unchanged, but second peak is changing, variable, okay. According to my theory and my formulas, this variability of second peak wavelengths changing, for this changing, relocating free electron motion forms direction, velocity and orientation are determinative, and for successive waves, variability and for that. 1. Compton experiment resultant peaks that seen on graphs. Okay. Show a certain deviation. These certain deviations indicate that there are certain determinative conditions. Deviator is a continuous spectrum. In spite of eliminating the continuous spectrum, all but a characteristic ray at a certain wavelength is involved in the continuous spectrum, and in spite of selecting only a characteristic wave at a certain wavelength that is involved in the continuous spectrum by means of Bragg crystal filtering, angular variation of relocating free electron motion forms successive waves transferring to another side of Bragg crystal by continuous spectrum cannot be prevented. Yes, Bragg crystal cannot prevent transferring of variation of successive waves respect to relocating electron motion forms velocity, direction, angle, and orientation. Bragg crystal by continuous spectrum cannot be prevented. Continuous spectrum makes characteristic X-ray deviate. The reason for the continuous spectrum is free electron motion forms relocation. Because if a free electron motion form starts to relocate, whether accelerating or decelerating or inertial, its successive wavelengths, velocity, and point energies change with respect to free electron motion forms velocity in the direction of 0 degree, remember, in the direction of 180 degree, in the direction of 90 degree, in the direction of 90 degree, unchanged, I agree now, okay. Step by step, I advise you to watch my video step by step. Again, because if a free electron motion form start to relocate, whether accelerating or decelerating or inertial, its successive wavelengths, velocity, and point energies change with respect to free electron motion forms velocity, relocating direction, angle, and relocating orientation. Here, free electron motion forms relocating direction 0 degree here, for instance. For this, I have put forth some formulas, and these formulas are determinative of Compton's experiments results. By the way, the Bremsstrahlung concept and explanation for continuous spectrum are invalid. Could characteristic X-rays seen in graphs as shown in the Compton experiment if they were independent of the continuous spectrum? I'm so sorry, my sketch. I must erase you. Yes. Yes. Could characteristic X-rays here continuous spectrum? Remember, this is intensity or energy derivative. Here, wavelength. Okay. This is continuous spectrum of successive waves of free electron relocating free electron motion form. Could characteristic X-rays seen in graphs here? This is characteristic X-ray line on the graph. This is continuous spectrum. Okay. From successive waves variation for relocating because of relocating free electron motion form. Could characteristic X-rays seen in graphs as shown in the Compton experiment here? This is filtered characteristic radiation. Okay. Here, continuous spectrum. Front of crystal, continuous spectrum. Before filtering, continuous spectrum. And here, characteristic ray at this point. Okay. But we now wholly turn around the crystal on the fact. Okay. Could characteristic X-rays seen in graphs as shown in the Compton experiment if they were independent of the continuous spectrum? If in this experiment were caught the characteristic X-rays were absolutely solidly, would they seem on the graph as these peaks? If the photon and at rest electron colliding was the reason for these peaks, in everyday life we would see the same X-ray peaks in graphs from in every X-ray experiment without Bragg crystal. 2. Experiment proposal. If we manage to make free electron motion form at rest, it will produce and propagate same wavelength and same velocity successive waves, and there will not occur continuous spectrum. But I guess if this free electron motion form's wavelength is greater than single wave pulses wavelength, and if they are intertwined, and if these intertwined waves pass the Bragg crystal that is arranged to filter single wave pulses wavelength, as a result we will see that the two different light types interacted, and we will see the two peaks, one of at single wave pulse wavelength, another one at single wave pulse plus 2.0022 nanometer. Why? Remember, we added the 0.0022 nanometer flexible constant here, if you see. I guess you'll see. Here. delta lambda chi 0.0022 nanometer. They say Compton wavelength. Okay. Remember, we added the 0.0022 nanometer flexible constant to single wave pulse here. This is single wave pulse's wavelength as intertwined with successive waves. Here, single wave pulses wavelength plus lambda here, lambda. Wavelength of representative single wave pulse plus 0.0022 constant. We say delta lambda chi or Compton wavelength. Another name, okay. Here formulas for single wave pulse from, Remember, we added the 0.0022 nanometer flexible constant. We added to single wave pulse wavelength when they filtered and seamed from Bragg crystal. When they filtered, here, single wave pulse wavelength and plus 0.0022 is equal to 0.0731 nanometer here, normal. Okay. After filtering the crystal, this is original peak, original X-ray characteristic wavelength, 0.0709. Okay. In this direction, these two different kinds of light velocities are the same, c. In this direction, relocating free electron motion forms wavelength is at its initial wavelength, and in the 90-degree direction, it doesn't change here. Okay. If we get the same conditions for all directions, we must make the free electron motion form at rest, and then we make these two kinds of light intertwined, provided that the single wave pulse wavelength is smaller. 3. If we notice, we see the two peaks are not separated in graphs. Not separated. Okay. Two of the peaks are in a continuum. 4. Fact 1. Provided that lambda normal of free electron motion forms successive waves is greater than single wave pulses wavelength, if free electron motion form is at rest and two successive waves intertwined with a single wave pulse, while lambda normal of free electron motion form successive waves are unchanged before filtering side of the crystal, second peaks of single wave pulses. Second peaks of single wave pulses, we say lambda representative single wave pulse I alpha, like this, here. I will explain in detail next. Okay, then. And second peaks of single wave pulse. Yes, waves intertwined with a single wave pulse, lambda n, of free electron motion from successive waves change as lambda alpha equal to lambda n minus delta lambda cosine alpha before filtering side of crystal, changing together. And second peaks of single wave pulses, lambda representative single wave pulse intertwined alpha changed as this formula here. This is changing formula. Okay. Yes. Now, here we are. These are wholly my formulas and my formulas relationships. Starting point, lambda n equal to 0.22 nanometer. For free electron motion forms lambda. Remember, we applied the electron motion form, this radius free electron motion form, say 20 keV, 20,000, 20 keV, and it was my formula, remember? This is lambda n minus delta lambda. I computed from my formulas 0.06135. Okay, then we find delta lambda for successive waves of free electron motion form. Here 0.15, etc. Frequency constant, and we find the free electron motion forms relocating velocity 216,340 point, etc. This one. Okay, and go on. For each angles we can find for here, for this point, for 0 degree, for 45 degree, for 90 degree, for 180 degree, for 30 degrees. Okay, we can find it's changing successive wavelengths and changing wave velocities like this here. Okay, and then here this column for this side for relocating free electron motion form successive waves continuous spectrum, for continuous spectrum here, relocating free electron motion forms formulas. These formulas front of, before filtering side results. Okay, here these results behind of crystal results and graphs. Okay, after filtering there's two different views. There are two different views. One of successive waves, continuous spectrum side, before filtering from crystal, and another for that intertwined with successive waves, single wave pulse, but provided that it coincides with variable continuous spectrum of successive waves from free electron motion form, relocating free electron motion form. Okay, then after filtering behind of crystal, results concern single wave pulses, peak shifting. Okay. Then, for, say, 0 degree, if we apply this formula that I put forth, we get only 0.0709 nanometer this pulse, single wave pulse. And here, for successive waves before crystal filtering, front of crystal concern successive waves of electron motion form, lambda 0 degree is equal to this result, and its wave velocity equal to this velocity. Okay, 83,659.09 kilometer per second, for example. What about 45 degree? This side we compute with these formulas. This side for successive waves from relocating free electron motion form. For here, this point, okay, 45 degree. On this point, its wavelength is 0.1078 nanometer, and it's this at this point, it's at 45 degree point. Wave velocity of successive waves of free electron motion form is 147,025.3 kilometer per second, like this. Okay, and for shifting of